Section 4 is talking about normal force, officially. So normal force, as we know, is always directed perpendicular to the surface of contact. So if we're on a horizontal surface, it will be perpendicular to that, directed up. But if we're on a tilted surface, so like a hillside or something, it will still be perpendicular to that surface, so it won't be directed up anymore. Okay, so you got to keep that in mind. It always adjusts itself so that the object stays on the surface without falling into the surface. So we got to keep that in mind also. The normal force is not necessarily exactly the same as the weight. It will adjust itself so that we stay on the surface without going into the surface or without floating away from the surface. So we have an example sitting here right off the bat. A 1.2 kilogram book lies on a table. You press down on the book from above with a force of 15 newtons. So now we want to figure out what the normal force acting on the book from the table below would be. So we're going to draw a little free body diagram to get started on this one. All we really need here is the free body. So here's the book. And then we have obviously the weight of the book, as we learned last time, would be directed down. So we have the weight, and that would be turning into mg eventually. But we also have this force directed down. Okay, so that's directed down, and we can call that capital F. And of course that's in the y direction. So F sub y maybe. And then we would have the normal force directed up. And since the book is not moving, the normal force, that's a lowercase n, would be equal to the sum of these two forces, weight and F sub y, okay? So since the book is not moving, the F net, so that's a capital F, and then sub net, we're a little bit lagged here, so that's why that looks like that, net. So F net would be 0. We're not moving. Okay, so then what we want to do is have a sum of the forces. Since we only have forces in the y direction, sum of the forces in the y direction. And so what do we have? So the normal force is positive. Nope. Minus the weight, because that is in the down directions, that would be negative. And also minus F sub y, because that is also in the down direction, so negative. And that's it, right? Okay, but F equals ma. So mass times acceleration in this case, we have an F net of 0, so this would equal 0. All right, so what can we do? Since we're looking for the normal force, we can solve for n. So I'll add weight and add Fy to both sides. So we have n equals positive weight now plus Fy. Okay. Now we know that the 1.2 kilogram book lies on the table. That's going to go to the weight, but it is not the weight. How do we figure out what the weight is? Okay. So the normal force would be mg, the mass of the book times gravity, and then plus the force in the y direction, which we are told is 15 newtons. That's the force that we're applying. So we can now plug in the stuff. We have 1.2 kilograms times 9.8 meters per second squared, because that is gravity. And then we have plus the 15 newtons. And what do we get for the normal force? $26.7 something? Okay. If we have two significant figures, so 26.7 something would be what? 27 newtons. All right, so pretty straightforward problem on that one. So commonly, we're going to be dealing with things that are on some kind of a ramp or incline anyway. If we are ignoring friction, then there are only two forces that are going to act on the object. That's going to be weight and the normal force. So we'll carefully work out the components of these forces to solve our dynamics problems. So a typical ramp problem will have this sort of free body diagram. We'll have some angle theta, and as we have seen, the angle theta that the ramp is making will correspond to this angle right here on the free body diagram. So these will be linked, okay? And if you're ever not sure, just take the angle of the ramp. So the angle of the ramp, and what we're going to do is make the angle of the ramp super tiny. And when you do that, then wow, I'm going to redo that one because that was terrible. The angle of the ramp being super tiny makes your perpendicular angle make it very obvious. Like if I go back to this angle theta right here, it makes things very obvious when you break things into components where that angle theta has to be, okay? So like the angle theta clearly is sitting right here because our angle theta is sitting right there. Those are super skinny angles. So that's kind of how I remember how these angles have to go. So these are clearly corresponding angles here, clearly corresponding angles here and here, okay? So anyway, just over-exaggerate the drawing, and that will help you understand where those corresponding angles are. So when we rotate the x-axis, match the surface, to match the angle between the weight and the negative y-axis, that's how you're going to do that, okay? The weight force always points down. As we've talked about, the weight will be decomposed in x and y components. So I'm over here on the right-hand side now. So we're going to break the weight vector into weight in the y direction and weight in the x direction. You definitely want to do that right away. Break those into components, and then you will see the normal vector and the weight in the y direction. And then we have this weight in the x direction. And the weight in the x direction is actually going to be the part that causes the net force and acceleration down the hill or ramp or whatever it is. So then we take a look at this one. The mountain biker is climbing, that's important, a steep 20-degree slope at a constant speed. The cyclist and bike have a combined weight of the 800 newtons. So then we have the figure that we were just looking at for guidance. What can you say about the magnitude of the normal force of the ground on the bike? So then you have three choices there. We got to think about this for a second. It may not be totally obvious what the answer is. Think about it. Maybe help yourself by drawing something. The best way to solve this problem is by drawing a picture. The picture would be a free body diagram. So first thing we're going to do is we have bicyclists going up a hill. So we're going to tilt our axes. So this would be my x-axis. And then because I have my x-axis tilted, my y-axis needs to be perpendicular to that. So I do my best drawing a perpendicular axis on my computer screen. There we go. So this is my y-axis, positive being in the sort of up direction. All right, so now my bicyclist is going to be dead center there. There he is. And what forces do I have acting on this bicyclist? Okay, weight vector is directed which way? Down. Definitely straight down. Okay. What else is acting on this bicyclist? Normal force is perpendicular to the slope. So that will be going directly up the y-axis. Okay, so I have weight vector down, and I have normal force perpendicular to the slope. Okay, what else is acting on this?
Just those two things. Some kind of friction, right?
Okay, probably some kind of friction. We haven't talked about that, but we're going up at a constant speed for sure, right?
Yeah.
Okay. So there's going to be some kind of force going up because he's trying to go up the hill, right?
Yeah.
Okay, so we have a force going up the hill. I'll just call it capital F. And then we have some kind of friction force probably coming backwards down the hill. Yeah? Okay. So some kind of friction coming down the hill. Okay. Call it lowercase f. All right. So now the next thing we're going to do is, somebody already said it, we're going to break that weight vector into components. We want everything acting along the axes. So the weight vector then would be broken into a component making a right triangle here along the y-axis. We'd call that weight in the y. And we would break the weight in an x as well. Again, making a right triangle there, okay? So that would be the weight in the x.
And since the
Now, we have the weight in the y and the normal in the y would have to add to what?
0.
Yes, because we're not floating away and we're not going into the ground. Those are the only forces that are acting in the y direction. They must equal 0 when they add, okay? And then we also have force going up the hill, the weight in the x direction and the friction in the x direction. Because the cyclist is bicycling at a constant speed, those must add to what?
0.
Okay, so our net force here in our free body diagram would be what?
0.
Okay, just to complete the free body diagram. Now, the question though is, what is the normal force based on these answers? Is it greater than 800, equal to 800, or less than 800? Well, if the weight, the combined weight is 800, the combined weight would be 800 right there. Okay? Now, the sum of the forces in the y direction tells us that this W sub y would equal the normal force. But what do we know about W sub y compared to W?
It's not equal to.
It's not equal to W. In fact, it is greater than, less than, or equal to W.
It's less than.
From what we know about right triangles, it is less than, because W in this case would be the hypotenuse of a right triangle. And the hypotenuse of a right triangle is the longest side. Therefore, W sub y is less than W, which means W sub y must be less than 800. And the normal force is the only other force acting in the y direction. Therefore, the normal force must also be less than 800. So logically, the answer must be C. That's how you work through a problem like this. You guys need to be drawing free body diagrams and looking at vectors. Okay, so that's how you do that one. And moving on. Now that we've done that, a skier slides down a steep 27-degree slope. On a slope this steep, friction is much smaller than the other forces acting on the skier and can be ignored. What is the skier's acceleration? What are we going to do? Draw a free body diagram? Okay, so first let's try to understand what is happening in this problem. So we have this steep 27-degree slope. So if we're to draw a motion diagram, the skier is accelerating down the 27-degree slope. So our first dot would be here, our second dot would be here, our third dot would be farther, our fourth dot would be farther. So the motion diagram would show velocity vectors getting longer and longer and longer, right? Okay. So we'd have our these are velocities. So we draw the velocity on there, that's a V. And then we would have an acceleration as well. Going which way? So we have an acceleration vector going in that direction. Okay, so now because we have an acceleration vector going in that direction, we already know that we have a net force going in that direction as well, okay? So now if I draw a pictorial representation of this, I would be drawing my hill, okay? And then I'd be drawing my skier. So we got our little skier guy, amazing drawing. Drew it too small to draw a happy face, so there you go. And now what do we do? This is just a pictorial overview, so I got my picture. What do I do now? I circle it. Okay?
Look at that, he's touching the ground.
And then what happens?
Yeah, identify all the forces.
Identify all the forces. Good. So what forces are acting on this guy?
Wait,
Okay? So we have a weight directed which way?
direction down,
Okay? And what else is happening?
normal force,
A normal force directed which way?
perpendicular.
Perpendicular to the surface. So the normal force would be kind of like this. What else is happening on this guy? Anything? What's that? Is there? Friction is ignored.
We can also probably drag too.
Friction is ignored.
This drag is friction in the No,
He's got a rocket strapped to him for thrust? Okay.
yeah, it would be cool.
Any other forces? No.
But we need to, where's
That's
this
it.
weight?
Weight is there already.
No, excuse me.
Okay, so now we can draw our free body diagram. So how do I start this? Tilted axes. Okay, so I have my x-axis, that's my hillside, and then my y-axis perpendicular to that. So here's x. I'm going to call my x down the hill positive, and then my y-axis up is positive. Okay, now my skier is dead center. And I'm going to draw my vectors now. What am I drawing? Weight vector directed straight down towards the center of Earth, W.
And normal force on the way.
Normal going directly along the y-axis. Okay, and what else should I draw on here? I'm not done with my free body diagram yet. F net is directed which way? Down the slope. We know that it's directed that way because of the acceleration vector here that we drew. So F net is directed down the slope. Okay, so now somebody already said we can break the which vector into components?
Wait,
The weight vector. So the x component will form a right triangle, and the y component will also form a right triangle, which we can put along the axes like so. So this would be weight in the x direction, and this would be weight in the y direction. We're also missing one thing, the 27-degree angle. So the 27-degree angle would be down here, 27 degrees. Now the question is, where is the 27-degree angle on the skier? Yeah?
is it between the WX and the W?
Is it the WX and the W, or is it the WY and the W?
That's the WX and the W. No, yeah, that's right.
I'm gonna agree
With who?
between the W and the WX.
Between the W and the WX? So you're talking right there? Oh, you can't see that, can you? Are you saying right there?
Yeah.
Yeah. We're like, yeah.
Did you see that dot?
Yeah.
Okay. Is that it?
Yes. No, for sure, he's probably.
It's one of the two.
All right, so it is actually here. So we need to mark that. This is 27 degrees here. Terrible job of writing 27, but that's 27 right there. I know, I drew a small picture. It's terrible. Okay, so now that we know that, what we're going to do is we're going to make our right triangle here. Okay, and we're going to make that WX there. okay? The reason I'm doing that is because now I can use this 27 degrees that's in that corner with my right triangle, and I can say that W sub y, or I can say, sorry, using this 27 degrees, I can find W sub y and I can find W sub x. So if I want to find W sub x, let's say, then that will be the opposite side. So I'll be using sine 27 degrees equals W sub x, that's the opposite side, over W. Okay? And then I can turn that into, if I want to find W sub x, just multiply both sides by W, and I'll have W sub x equals W sine 27 degrees. And I can do the same thing now for W sub y. W sub y is on the adjacent side of 27 degrees. So that is cosine, adjacent hypotenuse. So I'll have cosine 27 degrees equals W sub y over the hypotenuse, which is W. And I will turn that into W sub y equals, multiply both sides by W, W cosine 27 degrees. Okay? So now I know what W sub x and W sub y are in terms of W, which I don't know anything about, but I know that W is actually mass times gravity, which I do know something about. I don't know anything about the mass, but I do know what gravity is. Okay? Okay, so now that we have that, what's our next move going to be?
Add gravity.
Turn W into mg?
Yeah.
Okay, we can do that. So then I'm going to rewrite these as W sub x equals, now W sub x is in the positive x direction, so that will be mg sine 27 degrees, perfectly fine. W sub y is in the negative y direction, so that will be, it will be negative mg cosine 27 degrees. Okay, we're paying attention to the direction that these vectors are going and making sure that we have the proper signs on them. All right, so now that we have those W sub x's and W sub y's, we're going to do our sum of the forces in the x and y direction. So let me do that over here. We'll do the sum of the forces in the x direction. What do we have?
You got WY, so.
X direction.
Oh, X?
All we have is the W sub x, right? W sub x equals, it's not 0. We have an F net in that direction, right? So we're going to write m times the acceleration in the x direction. By the way, what is it we're looking for?
Acceleration.
We're looking for the acceleration in the x direction, so that a sub x is what we're looking for, okay? Now, we want the sum of the forces in the y direction. What do we have?
Weight in the X direction.
We have the normal force in the up direction, so that'll be n minus w sub y. Okay, and then that's going to be equal to what? 0. There are no accelerations in that direction, so that equals 0. Okay, so now that we know all of that, what can we do?
We gotta solve for mass.
We have too many variables. Okay. So we know that w sub y is down here, negative mg cosine 27 degrees, right? Okay. So we can do something with that. We also know that up here, a sub x is sitting there, and that's what we're looking for. We know that W sub x is mg sine 27 degrees, yes? Okay. So there's something that we can do there. What can we do? What's that? But what equal? Let's substitute what we know in for the things that we're looking for. So like, for example, W sub x equals mg sine 27 degrees. Equals m a sub x, which is what we're looking for. Okay, now I can solve for a sub x by dividing both sides by m. And what happens?
Now it's just
Yeah, I have g sine 27 degrees, and g I know, a sub x. G is 9.8 meters per second squared times sine 27 degrees. So I actually don't even need to do anything with the sum of the forces in the y direction. What do we get? So we'll say, you said it was 4.44, so that's 4.4, because we only have two significant figures for that 27 degrees. 4.4 meters per second squared. So that would be the skier's maximum acceleration on that slope, ignoring all friction.
kind of slow.
They cannot accelerate faster than that. And notice what happened here. It did not matter what their mass was. So it could be the heaviest person, it could be the lightest person. This is their maximum acceleration. They could have the best equipment or the worst equipment. This is their maximum acceleration because the mass totally dropped out and we ignored friction. This is a frictionless situation, okay? The best skier, the worst skier, doesn't matter. So actually, we can extend this problem a little bit and say, what if we don't know what the angle is? If we go back here, we had g sine 27 degrees back here. What if we say we don't know what the angle is?
So it's g sine theta.
So then it's g sine theta. The acceleration down the hill, ignoring all friction, would be g sine theta. And that's kind of an interesting result. It doesn't make any difference what the mass is. It doesn't make any difference what the skill is. It doesn't make any difference at all what anything is. It only depends on what gravity is and what the angle is. Take away all the friction, and this is your maximum acceleration. It's kind of an interesting result, I think.
I would have thought you would have been a little faster than said for the 27 degree.
No, it's actually, that's it. So there you go. Kind of a very interesting deal, I think.